So you can see my screen, right? The screen is visible to all of you.
Yes, sir.
Okay, okay. So in the previous class, I mean, there was this problem about marbles on a staircase. So what we had was that there were n number of steps on the staircase and we had n marbles on them. Okay, so there are m steps and n marbles, and we had to arrange the marbles on the staircase such that each step is associated with a particular value of potential energy. And so I'm given a value of potential energy equal to U. And the question that I ask is, how many arrangements of these marbles can give me this potential energy value of U? So this how many number of arrangements, this is basically the number of microstates which the system had. And if I count the microstates, I will get the entropy. Now, whatever problems we had did in the last class, that involved a finite number of marbles and a finite number of steps. So basically what we could do is that we could outline the solutions, and in that way we could calculate how many solutions will satisfy the constraints of the total energy and the total number of particles. In that way we calculated the entropy. But what if there is an infinite number of marbles or infinite number of steps? Then how do we proceed with the problem in that case? So a good way of proceeding with that kind of problem is to use this generating function method. Okay, so this is like an analytic way of finding the entropy of the system. So we will take the example of the staircase only, which I had mentioned earlier. So there are capital N number of marbles on an infinite staircase arranged in such a manner that the total potential energy is equal to U. Okay, so the constraints are that the total number of marbles, that is summation of nj, where j is the step and j goes from 1 to infinity. So summation over nj is equal to n. So this is the constraint on the total number of marbles plus and this is the constraint on the total energy. So if j is the energy associated with the jth step, then the uh, energy associated with that step, if there are nj number of marbles, is j into nj. And if I sum over all these energies, then I will get the total potential energy. So these are my constraints. So if my microstate satisfies these constraints, then it will belong to that particular microstate which I'm looking for. Okay, so I define a quantity like this. So z of n is equal to delta of u minus summation over j into nj comma 0 into delta n minus summation j nj comma 0. So this delta, as you know over here, is the Kronecker delta function. So how do I define a Kronecker delta function? It is defined as delta m comma m is equal to 1 only if m is equal to 0. Otherwise it is equal to 0. Okay, so basically if these two indices are equal, then this delta function is equal to 1. If they are not equal, then the delta function is equal to 0. Right. So in some sense, you will see that if my microstate satisfies the constraints of total energy and total particle number, then this will be equal to 0 and this will be equal to 0, right? So then this delta function will be 1 and this delta function will be 1 and their product will also be 1. So Z for that microstate is equal to 1. On the other hand, if the microstate does not satisfy these constraints, then one of the two delta functions will be equal to 0. So Z will be 0 for that microstate, right? So if I sum over Zn, okay, considering all microstates, then basically I'm adding 1 plus 1 plus 1 up to the total number of microstates which give rise to this my particular macrostate. In this way, we can count over the number of microstates with the help of this function. Okay, so this part is clear, right?
Yes, sir.
Okay, so we define generating function like this in this manner. A function of the variables x, it is defined like this. So if I put x equal to 1, then I get this thing which I told you earlier. that I basically sum over all the microstates. I count the microstates, and this gives me the total number of microstates that my system has. Okay, so once I know the total number of microstates of my system, then I can calculate the entropy by simply taking the logarithm of this quantity over here. Right. So in some sense, it is like a microcanonical partition function. Why microcanonical partition function? Because it takes into account the microscopic properties of the system. All right, and partition, this word comes in from the fact that you're dividing a macrostate into different number of microstates. So all these different arrangements correspond to different partitions basically. So that's how this nomenclature comes in of the microcanonical partition function. So that's a different story. So the main point is that I can define my entropy like this by basically summing over these values of Z. Okay, now once I have my Z and my Gx, then how do I calculate this thing? Because we don't know the exact forms of these delta functions. So we do a trick. We write the delta function in terms of its Fourier transform. So for those of you who are not familiar with the concept of Fourier transforms, is that any function can be written in terms of an integral representation of its various modes. So for example, a Fourier transform of the sine wave gives the frequency associated with the sine wave. So basically, you can write it in terms of an integral of an exponential, complex exponential. In this way, the delta function can also be written in terms of its Fourier transform. So the Fourier transform of the delta function is actually 1 over 2 pi. So that's why this factor of 1 over 2 pi comes in over here. Integral of 0 to 2 pi d theta e to the power I theta k. Okay. So if I'm able to write the delta function in this manner, then if I substitute this value in place of these values over here, that is in place of z, then I get z is equal to two integrals. One is for the delta function concerning the energy constraint, and the other integral, it is for the delta function which satisfies the number of particle constraints. Okay, so you have two integrals going from 0 to 2 pi over the two variables theta and phi, so d theta and d phi. Factor of 2 pi square because of the two integrals coming in. And then you have basically k is basically these two quantities. So 1k is this one and the other k is this one. And if I substitute for them over here, then I get two exponentials e to the power I theta u and e to the power I phi n into the exponential of this quantity, which is the summation over j nj plus another term which comes in with phi, that is the summation over nj. Okay, now a summation which is there in the exponential can be written in terms of a product. So I write this in terms of this product, right? Now in the definition of gx, there was this summation over the number of microstates. Okay, so that is why the summation factor comes in, and then gx can be written in terms of this entire formula, where basically I have taken I common from these two factors and I have replaced the summation in the exponential by a product over these exponentials. And there is this factor of x to the xj to the power of nj, which was already there in my expression of gx. Okay, all right. So I can write the product of sums, I mean the sum of products, as in terms of a product of sums. And then what I get over here is basically a geometric progression series, a GP series, right? An infinite GP series. So a summation of an infinite GP series is a very well-known thing. So basically, if you have a series like e to the power x, e to the power x into some quantity, going from 0 to infinity, then this summation actually turns out to be 1 by 1 minus that quantity. All right, so that is what we have done over here. So we have written this summation in this particular form. And so this is the final expression of gx which I get. Okay, and now if I put x equal to 1 in place of gx, then I will get my zn. And if I take the logarithm of that, then I will get the entropy of the system. All right, so till this part the derivation is clear, right? Okay. All right. So so in this derivation, I had considered that the energy of the jth step is equal to j, right? So instead of j, if it was some general value equal to epsilon j, then basically I will replace this j over here with epsilon j. All right. So then, like I said previously, Zn is summation over Zn is basically gx equal to 1. So if I put x equal to 1, I will get the total number of microstates, and then the that will be basically exponential of my entropy. So in this way, I can write an analytic form of the entropy for an infinite staircase, marbles on an infinite staircase. And what you will see is that this is nothing but the entropy for a system of n identical bosons which are distributed among the energy levels epsilon j such that the total system energy is U. All right. So in starting with this problem of marbles on an infinite staircase, what we ended up with is that the entropy of a system of n identical quantum particles, basically a ideal quantum gas, such that the quantum particles are distributed among various energy levels of different energies epsilon j, where the total energy of the system is equal to U. So starting from a very simple example, we are able to derive something which is has a lot of physical relevance. Okay. So if there are any questions, you can go ahead and ask me now. Okay. Are there any questions?
No, sir.
Okay. Okay. All right. So an important thing which I must tell you now is that in this example, we had no constraints on as to how many marbles should be there on a particular step, right? So we could keep any number of marbles on a given step. So this basically corresponds to the fact that the marbles are bosons. Now, what if marbles are fermions? So if the marbles are fermions, then there comes the constraints that on a given step, I can have at most one marble or no marble at all. So two marbles cannot occupy the same energy state, right? Basically, what defines the statistics of fermions? This is one of the constraints on them. So if that is the case, then this summation over n, this GP series summation, this would no longer be an infinite GP series. This will only have two terms corresponding to nj equal to 0 and nj equal to 1. So basically it will be a sum over two terms. So this will be 1 plus e to the power minus I theta epsilon j e to the power minus I phi. Okay, so that is what we get over here. So if there were fermions, then this would be the exponential of the entropy of my system. All right. So given this expression, equation 7 and equation 6, I can write a general expression for the entropy of n identical quantum particles. That is, e to the power s is basically a double integral over theta and phi, e to the power I theta u, e to the power I theta n into fq of theta and phi, where f of q is equal to a product of j equal to 1 to infinity 1 plus q into e to the power I theta epsilon j into e to the power minus I phi raised to the power of q. So you see that in the simple expression, if I put q equal to 1, I get the expression for fermions, that is equation 7. And if I put q equal to minus 1, I get back equation 6, which is the expression for bosons. All right. So in this simple formalism, I can write the entropy for in general for a system of n identical quantum particles. Okay, now we go on to define what is known as the thermodynamic limit of the system. And with this definition, we will see that it will be easier for us to evaluate this particular integral, because in this current form, this integral is usually very difficult to evaluate exactly, or it may not even have a solution. All right. So what we do is that we define certain quantities like a specific energy. That is the energy per number of particles. Total energy divided by the total number of particles. Then we can write This and we also define another quantity called h of q. Okay, so we write f of q as e to the power minus I capital N into h of q. Okay, and then what we get is that this e to the power s, this becomes a double integral over d theta d phi divided by 2 pi square e to the power n into wq, where wq is equal to I theta u coming from here. Small u, basically why I have taken small u, because I have taken n common outside the product. That's why this is basically I theta capital U by capital N, which comes out as I theta u, plus you have another term which is I theta phi after taking n common, plus you have a term which is equal to hq. Okay, and hq was defined in this manner from f of q. All right, so in this way I can write a simple expression for entropy. Now, how do I evaluate entropy if it looks like this? It has this particular form. So we go to this thing known as the thermodynamic limit. Now in the thermodynamic limit, we take the number of particles and the total energy going to infinity in such a manner such that the small u, that is specific energy, is finite. So this is a very important point of thermodynamic limit, that we should take capital and capital U going to infinity in a manner such that small u is finite. Okay, so in order to evaluate this integral in the thermodynamic limit, what we make use of is known as the method of steepest descent or the saddle point method of integration. So what is the saddle point method of integration? So if I have an integral I, which is integration over dz e to the power n into gz, and if I take the limit n going to infinity, then the integral tends to e to the power n gz star, where gz star is a saddle point of this function gz. That is, it corresponds to an extremum of the function gz. Basically, g dash z at z equal to z star is equal to 0. So in saddle point method, what we do is that we replace the integral by the value of the integrand at its extremum value. Okay. So now let us suppose that this particular function wq has an extremum value at theta star comma 5 star. Okay. Now if I apply the saddle point method to this integral, then what I get is that e to the power s is equal to e to the power nwq at theta star and 5 star, where del wq del theta is equal to 0 and del wq del phi is equal to 0 at the saddle point, which is given by theta star and phi star. Okay, so then from this we can read off the value of entropy as S of u comma n is equal to S of un, small un comma n, which is equal to nwq, right? And so this expression also tells us something which we had covered in the last class, that is the entropy is an extensive quantity, and it will be extensive only if WQ is an intensive quantity. All right. So here is something which we had covered in the previous class only about the extensivity of entropy. So I won't go through it again. You can take a look at it if you want. So basically from the extensivity of entropy, and if I use the first law, then I get these important relations that del S del U is equal to 1 by T, del S del V equal to P by T, del S del N is equal to minus mu by T. Okay. So this method of steepest descents and thermodynamic limit. So these two things are clear, right? How I went from an abstract expression of entropy, then I simplified it, then I went to the thermodynamic limit, then I used the method of steepest descents in order to calculate the entropy. So you see, step by step, I went on simplifying my problem till the point where I can use approximate method to find out the entropy of the system of n identical quantum particles. Right. So till this point, is it all clear?
Yes, sir.
Okay. So then I will move on to the derivation of the Bose-Einstein and Fermi-Dirac distributions and the equation of states for ideal Bose and Fermi gas. Okay. So we had seen that f of q, this expression which we saw over here, it is equal to e to the power minus I n hq. So hq is equal to I by n log of f of q, right? So I can expand this logarithm, and then it becomes because f of q was given over here in terms of this product, right? So if I take log of f of q, then it turns out to be q into summation over j log of this quantity. So that is what I've written over here, iq by n summation j log of this quantity. Now since s is equal to u comma s of u comma n is equal to nwq, and wq can be written in terms of as you saw earlier, that is WQ is evaluated at this saddle point. So this is equal to IN theta star U plus phi star minus HQ evaluated at theta star phi star. Okay. Now I use these expressions in order to express theta star and phi star in terms of what is known to me, that is the temperature, the chemical potential. In terms of these quantities, I want to express the values of theta star and phi star. So how do I proceed with that? For that, I take a derivative of s with respect to u first. So del s del u is equal to 1 over t, which I saw earlier. So if I evaluate del s del u, then it turns out to be I n del phi star del u, okay, plus I theta star when I take the derivative with respect to capital U, plus I capital U into del theta star del u when I take derivative with respect to theta star, minus I n del u of HQ. Okay. So first we try to look at this quantity. We can break the HQ into different parts and then evaluate the derivatives. After evaluating the derivatives, we can break HQ into different parts, right? So if I take the derivative of HQ with respect to Q, then basically, since it is a logarithm over here, it becomes 1 over this quantity, plus you have a derivative of theta star with respect to u, which comes in with this term of epsilon j, plus a derivative of phi star with respect to u. All right. And then you get this form of the del hq by del u. Okay. So then if I substitute this value in this form, then also I will get a complicated equation, which is still very difficult for me to solve. Right. So how do I simplify this further? So in order to simplify this, we look at the constraints that WQ is a saddle point. Okay, so if WQ is a saddle point, then del WQ del theta evaluated at theta star phi star should be equal to 0. So if I solve this equation, then I can write an expression for u over n in this manner. All right. So in this way, I can actually express my capital U in terms of theta star and phi star and epsilon g. All right. This is doable. Similarly, if I take the derivative of WQ with respect to phi, okay, then this expression turns out to be nothing but del H del Q evaluated at this saddle point is equal to 1. So this again comes down from this particular equation itself. So from this, I can write an expression for n. So here again, I can express n in terms of theta star and phi star. Okay. So once I get n in terms of theta star phi star and u in terms of theta star phi star, I go back and take a look at this expression for del HQ del u, which I got over here. All right. So there are two terms in the summation. The first term is epsilon j del theta star del u divided by this quantity. And you see u is equal to this thing itself. So this is epsilon j divided by that quantity, right? So then this becomes q square by n u into del theta star by del u. All right. So basically you have del theta star by del u, and this entire quantity is equal to u. Similarly, if I take this other term over here, okay, then I get 1 over n del phi star del u summation over j 1 by this quantity. And in doing this, I had dropped off q square. Why? Because q can take values of only -1 and +1. So q square is always equal to 1. So I take q square equal to 1 and I get this expression. So you see, after I calculate the value of u and n from the saddle point constant of wq, I can actually get a simple expression of del hq by del u, which is equal to u by n del theta star del u plus del phi star del u. Now, if I substitute this expression into this equation over here, then what I get is this thing. And as you can see from this term and this term cancels out, and this term cancels out, and I'm left with I theta star only. So then 1 by t is equal to I theta star. So this tells me an important thing, that this quantity of theta star, it depends only on temperature and nothing else. Okay, and using this fact, I can also obtain phi star. How? So the other quantity which the entropy dependent on was the total number of particles, that is capital N. Okay, so del S by del N is equal to minus mu by T, something which we had got from the first law and the fact that the entropy is extensive. All right, now S can be written as I theta star U plus I n phi star minus I n HQ, as we had seen earlier, that is S is equal to N into WQ evaluated at that saddle point. Okay, I again substitute the value of HQ over here. So S is equal to I theta star U plus I n phi star plus Q into this entire thing, which is equal to HQ. Okay, now I take a derivative of this thing with respect to N. So I had seen over here that theta star is only dependent on T. So theta star does not depend on N. So derivative of this term with respect to N is equal to 0. Okay, so I take the derivative of this term first. So this is equal to I phi star plus I n del phi star del N plus a derivative of this entire term with respect to N. And again, I use the fact that theta star does not depend on N. So I only take the derivative with respect to phi star and I get this form of a quantity. Okay, now if I divide the numerator and the denominator by e to the power minus I phi star epsilon j into e to the power minus I phi star, then I get this quantity to be equal to minus I del phi star del N summation j 1 by e to the power I phi star epsilon j e to the power I phi star plus q. And this quantity was nothing but capital N, as we saw earlier over here. Okay, so if this is capital N, then this term and this term cancel out because they have opposite signs. So del S by del N is equal to I phi star. And since this was equal to minus mu by T, so I phi star is equal to minus mu by T. So phi star depends on both the chemical potential as well as the temperature. Right. So as you, in this way, we can express theta star and phi star in terms of mu and T. Now we introduce a quantity which is known as beta. Beta is the reciprocal of temperature. Actually, in normal text or usually, beta is actually not 1 by T, but 1 by kBT, where kB is the Boltzmann constant. So here we have been working in terms of units where we had chosen kB equal to 1. So in general, kB is not equal to 1. But for the moment, let us work in those units where kB is equal to 1 for simplicity of expression. Okay, so since beta is equal to 1 by T, this I phi star is equal to beta, and sorry, I theta star is equal to beta, and I phi star is equal to minus mu into beta. Okay, so if I substitute theta star and phi star in the expressions of capital U and capital N, then capital U turns out to be summation over energy levels epsilon j divided by e to the power beta into epsilon j minus mu plus q, and n is equal to summation over j 1 by e to the power beta into epsilon j minus mu plus q. Now if I compare these expressions with the expressions of u and n which I had earlier, that is u is equal to summation over j epsilon j nj and n is equal to summation j nj, then I can see that nj, that is the number of particles in the jth energy level, it is equal to 1 by e to the power beta into epsilon j minus mu plus q. So this is what is known as the distribution function of the number of particles. So Nj tells me the average number of particles which are most likely to occupy the energy level J. Or in other words, it is the probability of a particle of occupying an energy level J. So that is why this is what is known as the distribution function. Okay, now if I put q equal to 1, I I think I messed up the notation over the yep, I messed up the notation over here. If q is equal to 1, it should be Fermi-Dirac statistics, and if q is equal to -1, it should be Bose-Einstein. Okay, so for q equal to 1, I would get the Fermi-Dirac distribution function, and q equal to -1, I will get the Bose-Einstein distribution function. Okay, so this is the physical interpretation of A, which I had to Nj, which I had told you earlier. So up to this part, the derivation is clear, right? As to how we obtain the distribution function starting from the entropy of a system of identical quantum particles. Yes, the method of saddle point integration, and then how we get this distribution function. So this part is all clear, right?
Yes, sir.
Okay, okay. So now we move on to find calculating the entropy of a Bose or Fermi gas. Okay, so previously we had entropy in terms of the unknown variables, which were theta and phi. Now we actually have the what theta and phi actually stand for. We actually calculated that. So if we substitute those values of theta and phi, we can calculate the entropy of a Bose or Fermi gas. All right, so substituting theta star and phi star in this expression, I get S is equal to beta into u minus mu n plus this term. Okay, and once I know this, I can also calculate the equation of state of an ideal Bose or Fermi gas. Right. So equation of state can be obtained from the first law of thermodynamics itself, that is Ts equal to u plus Pv minus mu n. From this, I can read off S as beta u plus beta Pv minus beta mu n. Okay, so I basically divide by temperature and I get this right hand side. So then beta Pv, it turns out to be equal to S minus beta u plus beta mu n, and S minus beta mu plus beta mu n is nothing but only this term. So beta PV is equal to Q into summation J log of this quantity. So I get an equation relating the pressure, volume and temperature of my quantum gas, right? Ideal Bose or Fermi gas. So this is the equation of state. Okay. So one more comment which I would like to make over here is that we had started from the microcanonical ensemble, but Bose and Fermi gases can also be expressed in terms of grand canonical ensemble. And unknowingly, which we had actually done something like that over here. Why? Because in deriving the properties of the ideal Bose and Fermi gas, we had assumed the entropy to be a function of U and N, where so that means the entropy is depending on U and U and N were fluctuating quantities over here. So if I change U, S was changing. If I change N, S was changing. While the fixed quantities which I had over here were chemical potential mu and the temperature T. Okay, so basically I work in a system where mu, the volume of the system and the temperature of the system are fixed. So my system is allowed to exchange particles and energy with the reservoir while keeping its temperature, chemical potential and volume fixed. And so this is what is known as a grand canonical ensemble. And in many textbooks, you will find that Bose-Einstein statistics and Fermi-Dirac statistics are mainly derived by considering a grand canonical ensemble. Okay. So that said and done, we can also calculate the statistics for non-interacting quantum particles in a box. So in the previous example, we had free bosons and free fermions. There were no boundaries. Okay. Now over here, the system is as follows. I have a cubical box. Okay. Each side of my cubical box has a length equal to L. So my volume is equal to L cube. And all my particles are confined within the box. All particles are indistinguishable particles. They do not interact with each other. The only interaction which they have is with the walls. So on hitting the walls, they bounce back. That means they are always confined within the box. So I can write a Schrodinger's equation to find the wave function of the particle. Now, all of you are familiar with Schrodinger's equation, right?
Yes, sir.
Okay, okay. So this must be a very familiar example for you then, because this is one of the basic examples which one starts with, that is a particle inside a box. So the boundary conditions in the box is that the wave function at the boundaries is equal to 0 and the derivative of the wave functions is also 0 at the boundaries. And if I solve the Schrodinger's equation with these boundary conditions, then my wave function psi, which is a function of x, y, and z, turns out to be 2 by L to the power 3 by 2 sine of nx pi x by L sine of ny pi y by L sine of nz pi z by L, where nx, ny, and nz are basically quantum numbers. So they are constrained to have only integer values. Okay. And if this is my wave function, then the eigenvalues of these wave functions are my energy levels. Okay, so the energy levels turn out to be Ek is equal to h cross square k square by 2m, where k square is nothing but kx square plus ky square and kz square, and kx, ky, and kz are written in this term. So kx is basically nx pi by L, ky is ny pi by L, and kz is nz pi by L. Okay. So an interesting thing which you notice over here is that the energy levels are discrete. So each particle can have only a discrete value of energy. The energy levels aren't continuous. They cannot have all values of energy. All right. Now, one thing you will notice over here is that the discreteness of these energy levels, that is the separation between the energy levels, it depends upon the length of my box. Why? Because the wave vector is inversely proportional to the length. So this is what basically determines how separated my energy levels are. If the wave vectors are larger, the energy levels are more separated. If they are smaller, energy levels are less separated. So if I now make the length of the box large, that is if I make L larger, then the ki's they become smaller and smaller. So basically by making the length of the box larger, I reduce the separation between my energy levels. Okay, in this way, I can slowly make the energy levels less and less discrete, and finally I go on to the continuum limit when I take L to be going to infinity. Okay, and when that happens, when L goes to infinity, then I can actually turn the summation, that is summation over the energy levels, into an integration. Okay, so this is the approximation which I will make now. So in this previous example, we had epsilon j to be the energy of the jth level, right? So in place of j, I now have the summation over these quantum numbers ni. So beta epsilon j is nothing but beta into h cross square pi square by 2 ml square into nx square plus ny square plus nz square. Okay, so these are the energies of each level. Now, I was saying earlier that if I take the separation to be the box size to be going to infinity, the separation between energy levels reduces, and I can replace the summation by an integration. Okay, so here is the theorem for doing that. So let a small f of lambda n, this is n, okay. So f of lambda n, suppose this is an even function. It is an important statement, okay. Even function for n belonging to only integer values. So even function means f of minus lambda n is equal to f of lambda n, and my lambda is a positive real number. Then if I have some function j of lambda which is equal to lambda into summation n equal to 0 to infinity f of lambda n, then in the limit of lambda going to 0, j lambda is equal to half of integration from minus infinity to plus infinity f of x dx. Okay, so now if I compare the expression of f of lambda n with beta j, okay, then I can see that lambda is nothing but beta into h cross square pi square by 2 ml square raised to the power half. So if this is the form which lambda has, and n is equal to nx square plus ny square plus nz square, and it can take all integer values from 0 to infinity. So then what I do is that I use equation 19. That is, look at equation of state first. Okay, so over here I had a summation over j over this quantity. All right, so I write the summation over j as a summation over ni. That is my quantum numbers here. into log of 1 plus q into e to the power minus lambda square nx square plus n by square plus nz square. Okay, so this is nothing but uh, beta epsilon j. Okay, so beta into epsilon j is equal to lambda square into this quantity plus beta mu. This is my right hand side, and on the left hand side I had beta p into volume. Here L cube is the volume of the box, so I substitute L cube in place of V. Okay, now we make the following substitution. You see a lambda has this particular form, so I can write lambda as C0 by 2, C0 divided by 2L, where C0 is equal to 2 into lambda L, or it is equal to this particular quantity 2 beta h cross square pi square by m raised to the power half. If I make this substitution, then what I get is that I can write, I replace L basically by C0 by 2 lambda. So on the left hand side, I have C0 cube beta into P, and on the right hand side, I have 3 factors of 2 lambda, and I can write the summation over Ni in terms of 3 separate summations, which is the summation of Nx, summation over Ny, and summation over Nz. Okay, now you will see that this form of summation is similar to what we get over here in this theorem, lambda into summation over F. And here also we have lambda into summation over something else. Okay, so that is why we can use the above theorem and convert all of these quantities into integral expressions. So basically the summations get converted into integrals like this over capital X, capital Y, and capital Z, where capital X is equal to lambda nx, capital Y is equal to lambda ny, and capital Z is equal to lambda nz. Okay, so that is why you have e to the power minus x square minus y square minus z square plus beta mu over here. Now let us define a vector R. So R is a vector in the Fourier space, or in the vector in the quantum number space. That is the space of nx, ny, and nz. So R is defined as x into x cap plus y into y cap plus z into z cap. Then you will see that x square plus y square plus z square is nothing but R square. So we substitute R square over here. So then the expression for the equation of state turns out to be this. So this is the equation of state for a system of identical quantum particles which is trapped in a box. Okay. In a similar manner, we can also obtain the expression for total energy and total I mean, we already know the total energy and total number density of particles. So we can define energy density as well as number density. Okay, using these quantities, and we can also obtain similar expressions. So that is what I have shown over here. So we had seen that U can be written in this manner as summation over J epsilon J by e to the power beta epsilon J beta mu plus Q. Okay, I multiply and divide by beta. So this is equal to 1 by beta summation over J beta epsilon J divided by this quantity. And this is nothing but 1 by beta into summation over J some function of beta epsilon J, like I had shown earlier. And beta epsilon J, as we had seen, was lambda square nx square plus ny square plus nz square. Okay, so this can be replaced by f lambda n, and the summation over J can be written in terms of summation over nx, ny, and nz, and in the limit of L going to infinity, we can replace this with the help of integrals. So you have this factor of lambda cube coming in because of the theorem which was stated earlier. And so this can be written as an integral of d cube r 8 lambda divided by 8 lambda cube. Okay, so then if I replace this integral in place of this summation over here, then u is equal to 1 by beta, which comes in from here, integral over d cube r by 8 lambda cube r square, which is equal to beta epsilon j divided by e to the power r square e to the power minus beta u plus q. Okay, so the energy density u by the volume is equal to u by L cube. So if I divide by L cube, I get a factor of 8 lambda cube L cube over here, and this is equal to C0 cube. So this is the expression which I get for the energy density. Okay, and in a similar manner, I can calculate the expression for number density from the total number of particles. So I again do the same trick. I replace the summation over j with summation over nx, ny, and nz, and then I replace those with the help of these integrals in the limit of the box size going to infinity, and then my number density turns out to be 1 by c0 cube integration d3r r square divided by the denominator which we had earlier. Okay, and similarly, like earlier, we can also write an expression for the entropy. All right, so in this way we can calculate the different properties or the statistics, that is the entropy, the number density, energy density, and also the equation of state for n number of identical quantum particles which are trapped in a box. The particles can be fermions or bosons, and depending on whether they are fermions and bosons, we can put q equal to 1 or minus 1. So is this derivation clear to you? It's all clear, right? Okay. Okay. So the question which we now ask is that, can we go into a classical, can we go on to derive the statistics for a classical ideal gas from these expressions of quantum ideal gas which we obtained here? So Max Planck had stated that there are ways of going from a quantum to a classical formalism, and there are three ways in which can be done. So this is basically what is known as the classical limit of a quantum system, and this classical limit can be obtained in three ways. One is if I take a Planck's constant going to 0. Okay. The second is if I take the mass of these particles going to infinity. And the third is if I take the temperature going to infinity or beta going to 0. But these ways of taking the limits, they have to be sensible. I mean, I can't just take the limits randomly and then if I end up getting a non-physical result, so that won't be a correct way of taking limits over here. Okay, so whatever I do over here, it has to be meaningful. So let us see whether taking limits like h cross going to 0 is meaningful or not. Okay, so let us take the expression for number density, for example. So if I take h cross going to 0, then I will basically have c0 going to 0, because c0 is equal to 2 beta h cross square pi square divided by m to the power half. Okay, now if this taking this limit has to be meaningful, then the density should be finite. Okay, it should not be infinite in this limit. So from this expression, we can read out the value of e to the power minus beta mu, which is equal to 1 by rho into c0 cube into integral of this quantity. Now, if you look at this expression over here, and if you say that c goes to 0 as h tends to 0, then you will find that this quantity becomes very large. Okay, and when this becomes very large, then the contribution from this quantity over here, it is almost negligible, that is insignificant compared to the rest of it. Okay, so we can drop off this quantity and then it simply becomes an integral over e to the power minus r square d3r. And if I break it up into these three integrals, then you can see I get a product of three Gaussian integrals whose value I know. So in the limit h cross going to 0, e to the power minus beta mu is equal to pi to the power 3 by 2 by rho into c naught cube. Okay, so I substitute this value over here in this particular expression of rho. Okay, and then I see what this gives me. So in the limit h cross going to 0, then e to the power r square minus beta mu plus q. So I can drop off the value of q again because this becomes very small compared to c naught over here. So this is equal to e to the power r square pi to the power 3 by 2 divided by rho into c naught cube. Okay. So then in the limit h cross going to 0, rho becomes equal to this thing, right? So I again get a Gaussian integral over here because the q term had gone away, and this is equal to pi to the power 3 by 2, and so I get rho equal to rho. So this shows that rho does not go to 0 or infinity in this limit. So this way of taking limits is actually self-consistent and hence it is meaningful. So now we go back to equation 17, where we had derived the distribution function for quantum particles. That is the occupation number nj equal to 1 by e to the power beta epsilon j e to the power minus beta mu plus q. Okay, I take the limit h cut going to 0 and substitute the value of e to the power minus beta mu in this limit. So e to the power minus beta mu is equal to pi to the power 3 by 2 by rho c naught cube. If I substitute this value over here, then I get limit h cross going to 0 nj is equal to limit h cross going to 0 1 divided by e to the power beta j into pi to the power 3 by 2 by rho into c naught q plus q. Okay, again, since this quantity is very large and this is equal to either plus 1 or minus 1, I can neglect this quantity. And then e to the power beta j I take in the numerator and I get limit of h cross going to 0 rho c naught cube pi to the power 3 by 2 into e to the power minus beta epsilon j. Now, since I'm considering classical non-relativistic particles, instead of having discrete energy levels, they will have a continuous range of energies. Okay, so their energy can be equal to p square by 2m, where a p square can be equal to anything, right? Because they are not constrained by any value. Okay, so epsilon is equal to p square by 2m over here. All right. And I know that c naught cube is equal to 2 beta 3 by 2 2 beta by m raised to power 3 by 2 h cross cube into pi cube. Now I define the volume element of my classical phase space as 2 pi h cut. Now this is a concept which I will be talking about later, but bear with me for some time so that so that you can get an expression for the distribution function in the classical limit. So if I consider 2 pi h cut to be the volume element of classical phase space, that is the volume element associated with the phase point, and if I multiply this by the number density, then the volume element multiplied by the number density would actually give me the total number of particles. Okay, and if so this is capital N, and I define f of p as 1 by capital N, limit of h cross going to 0 ng. So f of p is nothing but the probability of finding a particle in the jth energy level. That is the probability of finding a particle with momentum equal to p, because I consider p to be the momentum of the jth energy level. And this factor acts as a normalization factor which you have while deriving probabilities. Okay, so if I substitute this expression over here, then I can actually read off n from this expression, and then f of p becomes equal to beta by 2 pi into m whole raised to the power 3 by 2 e to the power minus beta p square by 2m. So this is the celebrated Maxwell-Boltzmann distribution function. Okay, so you see that by taking the classical limit of a quantum ideal gas, we can obtain the distribution function for a classical ideal gas as well. Now, this was a way of deriving the Maxwell-Boltzmann distribution from quantum by considering first starting with Bose-Einstein statistics, doing all the calculations for quantum particles. Then I take the classical limit of the quantum particles. Then I get this distribution. So this is the procedure we had followed up till now. But there is a more straightforward way and a more intuitive way, a logically intuitive way of deriving the Maxwell-Boltzmann distribution, starting from classical particles itself. That is not going to quantum before coming to classical. We can start directly from the classical particles itself. So that is what I will be showing you up next, which is known as the phase space approach. So before I start with this, are there any questions or queries? Any doubts or questions?
No doubt, sir.
Okay, okay. So now we move on to the phase space approach. This is like a classical approach. I mean, a more classical approach of doing this. So what do we mean by a phase space? So can anybody tell me how do we define a phase space? Yes. Okay. Okay, so let me tell what is a phase space first. So you must have seen this in your course in classical mechanics that if you have a harmonic oscillator, okay, it is defined by two quantities, its position and momentum, right? Now, if I map the position and momentum of the harmonic oscillator at every instant of time, then it traces out an ellipse, right, in the momentum position space, right?
Yes, sir.
Okay, so this momentum position space is what is known as the phase space of that harmonic oscillator. Okay, so I had considered this harmonic oscillator as an example, but in general, if you have any system and it is defined by a set of coordinates, some can be its position, some can be its momentum, some can be its energy or anything, then the set of all those coordinates of that particular system is what is known as the phase space of that system. For example, if I have a particle, then what defines my particle uniquely is its position and velocity, or rather position and momentum. Why? Because the particle can have mass also. Okay, so the phase space of the particles is all the possible values of position and momentum which my particle can have. All right. So if I have a system of n particles and my system is in d dimensions, I can have a two-dimensional, three-dimensional, or even a one-dimensional system, right? In general, let's say that small d is the dimensionality of my physical space. Then the dimensionality of the phase space would be equal to capital N into d. Because there are n particles, each has d distinct coordinates, right? So the dimensionality of my phase space is equal to n into d. Okay, so this part is clear. For example, if I have a particle in a three-dimensional space, then it can be defined by three position and three momentum coordinates, right? So I have 3 plus 3, 6 coordinates defining the position of one particle. And if I have n number of particles, then I will need a total of 6 into n number of coordinates to quantify my system as a whole. So this is the dimensionality of the phase space of my system. So with this knowledge, we will go on to derive the statistics of a classical ideal gas from the phase space perspective. Okay, so let us say that there are n number of non-interacting particles in a box of volume equal to V. Okay, such that the total energy of the configuration is equal to E. What do I mean by total energy of the configuration? That is summation over I equal to 1 to n, pi square by 2m is equal to E, where pi represents the momentum of the ith particle. Okay, and this energy E is nothing but the internal energy of the system. It is not being influenced by any external forces or anything. It is the internal energy. Okay, so given these constraints of the n number of particles as fixed, the volume of the box as fixed, and the energy, that is the internal energy of my system, as fixed, these three coordinates n, v, and e are fixed. So as you can see, this is where I'm working in the microcanonical ensemble. So microcanonical ensemble is somewhere where n, v, and e are fixed. Okay. So as I had mentioned earlier, the phase space of the particle is defined by its position coordinate, which is qi, and the momentum coordinate pi. Okay, so p-axis, q-axis, any point on this pq plane is represents the position, that represents the position and momentum of an individual particle. Okay, and what are the constraints on pi and qi? There are constraints. That is, qi should always belong to the box of volume v. That means qi cannot be any value such that the particle goes outside the box. Since the particle is within the box, the qi coordinate should belong to my box. And the what is the constraint on pi? Summation over I equal to n pi square should equal to 2me, because my energy is fixed. So the summation of the squares of all the momenta is fixed. So these are the two constraints on my phase space. So my phase space volume is constrained by these two factors. Now I define omega as the total number of microstates of the system. So as you can see, the macro state, it is defined by the volume of the box, total number of particles, and the internal energy, right? So the number of microstates can be written as a summation over a quantity x, where x is equal to 1 if the position and the momentum coordinates satisfy that macro state, that is, if they satisfy this constraint. Otherwise, x is equal to 0. So by summing over the x's, I can calculate the total number of microstates. Okay, so how do I go about this business now? So there are the contributions from the particle coordinates. So I have n number of particles and the volume of my box is v. Now these n particles can be in any position inside the box and they can be arranged in the different positions in v to the power n number of ways. Okay, so they can be arranged in different positions of the box in v to the power n number of ways. So this is one contribution to omega. And the other contribution to omega comes from the momentum coordinates, which is p. Okay, that is the momentum should belong to this high. So the momentum should follow this constraint. That means if I look at the three-dimensional momentum space, that is px, py, and pz, then if I, for simplicity, I'm doing three dimensions over here for explaining. So if I is equal to x, y, and z, then this expression is equal to px square plus py square plus pz square is equal to 2me. Now you see that this is an expression, this is an equation of a sphere in three-dimensional space such that the radius of the sphere is equal to square root of 2me. Okay, so any point on that on the surface of that sphere, it will satisfy this particular constraint. So all those points on the surface of the sphere contribute to my microstate. Okay, so I had talked of three dimensions. So in general, if the sphere is d-dimensional, that means it can have more than three dimensions as well, then it becomes a hypersphere. And in general, we get hyperspheres. Why? Because we are working with many number of particles. So even if small d is equal to d, n is a very large quantity. So the dimensionality of the momentum space is much, much greater than 3. Okay, so we have to find the surface area of the n-dimensional hypersphere, and that surface area contributes to the total number of microstates. So we define the area of that hypersphere as a underscore t, a subscript d. So the total number of microstate is equal to v to the power n multiplied by ad. Okay, so this is the total number of microstates. So up to this part it is clear, right? Any questions? Okay, so if there are no questions, then let's go on to see what this value of a of d is. So for example, if I take three dimensions, it is very simple. A of d is the surface area of a sphere, which is equal to 4 pi r square, where r is given over here. And if it is a two-dimensional phase space of momenta, then it becomes a circle. And then this thing becomes equal to the circumference of a circle. But in general, for d dimensions, what happens is that AD is equal to SD into R to the power D minus 1, where SD is the d-dimensional solid angle. Okay, now how do I calculate SD? I use Gaussian integrals to do this thing. So what is the trick? So let's define an integral ID as a product of d such Gaussian integrals, and this is equal to pi to the power d by 2. So if I rearrange this quantity, I can write ID in this form, that is product of I going from 1 to d dxi e to the power minus xi square, and there are d number of integrals over here. Okay, now I make a change of coordinates. I move on to the coordinates such that r square is equal to summation I equal to 1 to d xi square. Okay, so then some product of I equal to 1 to d e to the power minus xi square becomes equal to e to the power minus r square. All right. Now, since why is it possible to make this change of coordinates? because the integral is a spherically symmetric integral. It's a Gaussian integral, so it's spherically symmetric integral. So if I make the substitution, then the volume element, that is the product of I equal to 1 to d dxi, this is equal to the solid angle into r to the power d minus 1 dr. So this is a very general expression for a volume element in capital D dimensional space. Okay. So if I substitute this expression of the volume element and e to the power minus r square in the expression of id, then id is equal to 0 to infinity e to the power minus r square st r to the power d minus 1 into dr. Now if I substitute r square equal to y, so if I do the substitution, then I end up getting id is equal to st by 2 d by 2 minus 1 factorial, and this is equal to pi to the power d by 2. So from this I can read off st is equal to 2 into pi to the power d by 2 divided by d by 2 minus 1 factorial. So this is the expression of the solid angle in d-dimensional space. And once I know the solid angle, omega is equal to v to the power n sd r to the power d minus 1. Okay, so if I substitute this value over here, I get v to the power n, the value of the solid angle. R, as we saw earlier, was equal to root over 2me. So this becomes equal to 2me raised to the power d minus 1 by 2. Right. So I calculate entropy. I calculate the total number of microstates in this way my system can have. So all is good up to here. Any questions or comments,
sir.
if any? Okay. All right. So once I've got this value of omega, I can calculate entropy like I had done earlier. So for a microcanonical ensemble, we had seen that entropy is the log of the number of microstates into kb. So earlier we had taken kb equal to 1. Here we take kb not equal to 1. So kb ln omega, right? So I take the log of this quantity, and in order to simplify this particular factorial over here, I make use of Stirling approximation. What is that? Log of n factorial is equal to n log n minus n. Okay, so if I take the log of this quantity and I apply this substitution over here, and there is one more, I get this huge expression for S, which is this. Now, since I'm working in the thermodynamic limit, I take capital N going to infinity and also capital E going to infinity. So in this limit, my capital D, which is equal to small d into capital N, is also very large. So we neglect the terms which are not so large. So which are the not so large terms in this expression over here? Well, the ones which are not so large, we neglect those. All right, after doing the Stirling approximation, and if I do those things, then I arrive at this particular value of entropy, which is equal to nkb log v multiplied by 4 pi m capital E divided by dn in raised to the power d by 2, and this small e basically the exponential e. Okay, so this comes from the fact that there was dn by 2 over here. I can write this as dn by 2 into log of e, since log of e is equal to 1, and from that I get this small e. Okay, so this is the value of entropy which I get if my number of microstates has this particular form. All right, so if I take del s by del e, I know that del s by del e was equal to 1 by t. If I make the substitution over here, then E is equal to dn by 2 into nkbt. So if I'm working in three-dimensional space, I can replace small d by 3. Then the internal energy is equal to 3n by 2 nkbt. And also del s by del v is equal to p by t. And if I calculate del s by del v from here, I get the equation of state, which, as you can see, is the well-known equation of state for an ideal gas. Okay. And now I had shown you earlier that we had derived the Maxwell-Boltzmann distribution function from quantum particles. So with this classical formalism, that is by knowing the total number of microstates over here, we can also obtain the Maxwell distribution function, which is the distribution of the velocities or momentum of the particles. So the distribution function is defined over here as number of particles having a momentum p1, or the probability of a particle to have a momentum equal to p1. So here For simplicity, I choose d equal to 3, but in general, it can be done for any value of small d. Okay. Now, since this is the probability of finding particles with momentum equal to p1, this probability can be restated as the probability of finding n minus 1 particles whose total energy is equal to E minus P1 square by 2m. That is the probability, that is count. We have to basically count the number of arrangements of other particles. So this is actually a simpler way of doing this rather than finding the probability of a single particle having momentum equal to P1. An alternate way of doing this is that we find the total number of microstates of the other particles, which does not have momentum equal to P1. So basically, this is like a conditional probability. I'm fixing the momentum of the particle and I'm calculating the total number of arrangements which I can make with the other particles with the constraint that my given particle has momentum p1. Okay, so the total number of microstates which I can form with the other particles is given by this E minus p1 square by 2m v n minus 1. So these are the total number of arrangements which I can form with all the other particles, and this I multiply with a factor of v. Why? Because the particle of momentum p1, it can be residing at any point in my box. Okay, so for each point I have a combination of microstates. If it is at another point, I have another combination of microstates. And so if I incorporate all those contributions, I get a factor of v over here. Okay, divided by the total number of microstates, because this is a probability. So if I do this calculation, I break up, I know the expression of omega over here. I basically substitute in place of e minus p1 square in this expression, and I can calculate the numerator. And the denominator I had already obtained earlier. And if I use the Stirling's approximation and take the thermodynamic limit of n going to infinity and E going to infinity, then I arrive at this expression of F. Okay. And if I set E equal to 3 by 2 nkBT, which is the internal energy of an ideal gas in 3 dimensions, then I arrive at this equation, okay, which is the Maxwell's-Boltzmann distribution which we had obtained earlier. So as you can see, even from this phase space approach, which seems more logical, I can get the Maxwell's-Boltzmann distribution as well. Now here is a catch, which I had paused before and told you earlier to check whether everything is all right or not. So if so I have calculated this number of microstates over here, and from this I had obtained an entropy which looked like this. Now I know that the entropy is an extensive quantity. Okay, so that means that if I scale E by lambda E, V by lambda V, and N by lambda N, then S should become lambda S, right? But what do I see over here? If I replace E by lambda E, V by lambda V, and N by lambda N, then S becomes equal to lambda into S at EVN plus NKB lambda. So as you can see, this expression of entropy is not extensive at all. So there is a mistake over here. So can anybody point out what mistake I have made while deriving the expressions? Yes. Let me repeat the question again. So you know that entropy should be extensive, right? But if I use this expression of entropy over here, I substitute n as lambda n. In place of v, I write lambda v. In place of e, I write lambda e. And then I calculate the entropy. However, this new entropy which I get, this is not equal to lambda times my old entropy. It is lambda times my old entropy plus some extra factor which is not equal to 0. So the entropy is not extensive over here. Now can anybody tell me why the entropy is not extensive? Like what mistake have I made in this calculation of entropy in my derivation over here? Yes, anybody? Okay, so here is the concept of distinguishability and indistinguishability, which I had. In case of quantum, I had already considered my particles to be indistinguishable. But when I'm doing this classical approach, then I did not consider the particles to be indistinguishable. Because remember, when I had said that I can put the particles in the box in different positions in v to the power n number of ways. So I had written over here there are v to the power n contributions from all particle coordinates. Now there will be v to the power n contributions only if I can distinguish between my particles, right? If I can say that this particle is different from that particle, then if I interchange their positions, then I get a different configuration. In that way, if I calculate all contributions, then those turns out to be equal to v to the power n. However, my ideal gas particles are not distinguishable from each other. That means even if I interchange their positions by keeping their momentum same, they will have the same configuration. Okay, so in order to account for this indistinguishability, what I have done over here is that my mistake was that I had overcounted the number of particles. So I had overcounted the number of microstates, and that's why I had been getting a wrong result. So in order to correct for this overcounting, we divide by the number of permutations n number of particles can have. Basically, this accounts for the indistinguishability of the particles. So n number of particles can have n factorial number of permutations, right? So what I do is that I simply divide the expression of the number of microstates which I had obtained earlier by this factor of n factorial. Okay, and after dividing by n factorial, if I calculate the entropy, then you will see that the entropy has this form of an expression where there is a factor of E by N which is in the volume. So if I compare equation 32 with this expression over here, you see that the volume was not divided by any factor of N, and this was giving rise to the error. If I account for the indistinguishability of the particles, then I have to also incorporate this factor of n factorial, which leads to a division of the factor of v by n over here. Okay, now if I replace E by lambda E, V by lambda V, and N by lambda N, and I calculate the entropy, then you will see that S of lambda E, lambda V, lambda N is equal to lambda times the earlier entropy. Okay, so now this shows me that entropy is properly extensive, and this is the correct form of the entropy. And this expression over here is the correct form of the number of microstates of an ideal gas. Okay. So this is a very important takeaway message, and this is directly related to the Gibbs paradox, which is related to the mixing entropy of ideal gases. So are you familiar with the Gibbs paradox, all of you? Yes. Do you know what Gibbs paradox is? Anybody? Okay. So let me state the Gibbs paradox for you in simple terms. So suppose you have a big box, okay, and you have a partition in between the box. Exactly in between the box, you divide the box into two equal halves. You say that there are n number of particles in one half of the box, which has volume V, and the same number of particles are there in the other half of the box, which has the same volume. Okay. So here the ideal gas in one portion of the box has a given entropy. The ideal gas in the other portion of the box has a given entropy. Okay. Why do they have different entropies? Because they had different energies initially. So the number of particles and volume of each partition is fixed. Energies are different. So one partition has ideal gas at a given energy. Another has an ideal gas at another different energy. Okay, they have different entropies. Now, if I remove the partition and they mix together, then the question is, will I get any change in entropy? So the answer is no. There is no change in entropy. Why? Because even if my partition was there or was not there, I'm not being able to distinguish between my particles because all of them are indistinguishable. So the presence or absence of the partition over here has no physical meaning, right? So if I calculate the entropy by considering the indistinguishability of number of particles like this, then I will find the mixing entropy to be equal to 0. However, when this indistinguishability was not considered previously, when the particles were considered to be distinguishable, then it was found that on removing the partition, there was an increase in entropy upon mixing, which was known as the mixing entropy, which is actually a paradox which should not have happened physically. So they were observing it theoretically, but they were not seeing it physically. So in order to resolve this paradox, the indistinguishability of particles has to be taken into account. So indistinguishability can be taken into account in this way, which I have shown over here. And this is what is known as the Gibbs paradox. Okay. So if that is all clear, then I can discuss a few problems now. So let me see if you are familiar with this particular problem over here. So I had this system of ideal gas particles, right? There was no potential energy over here. They were free particles. So their energy was given by pi square by 2m. So they only had momentum. Now let us assume that there is a potential energy in the box. That means, for example, I consider which are subject to a Hamiltonian of this form. Okay. So this is the Hamiltonian of a harmonic oscillator, and there are n number of harmonic oscillators. Each of them are defined by the positions qi and the momenta pi. Okay. So we have to calculate the entropy as a function of the total energy. All right. So we proceed in the same way as we had done earlier. So the available volume of phase space is basically 1 by Hn. Hn is basically a normalization factor, which I was telling you earlier about the volume normalization of volume of a phase space element. If I consider that to be H, then I should normalize by 1 by Hn. And this integral gives me the total energy, total volume of phase space over here. Okay. This is the energy constant on the particle. So earlier, in case of ideal gas particles, my constant was this summation pi squared equal to 2me. So you saw that it gave me the surface of a sphere, which is a very general, which is a very simple thing, because a sphere is obviously much more simple, one of the most simple objects in 3 dimensions, right? So this gave me the surface of a hypersphere, and for that, if I know the solid angle, I can calculate the phase space volume from the spherical symmetry itself. That's what I've done over here. But over here, you will see that because of this factor of omega, this is no longer a sphere. On the other hand, it is an ellipsoid. Why? Because you know the equation of an ellipse in 2D, it is x squared by a squared plus y squared by b squared equal to 1. So the phase space, so the surface of constant energy in 2n dimensions is actually an ellipsoid in 2n dimensions. Why 2n dimensions? Position, momentum, 2 coordinates, total number of particles n, so 2n dimensions. Okay. So what is the surface area of an ellipsoid? So this is actually a difficult question to calculate analytically. Numerically, obviously one can obtain it, but analytically doing this integration will be difficult if we consider it to be an ellipsoid. All right. So what we do is that we make a coordinate transformation, which is also known as a canonical transformation. So we write root over m omega qi as qi dashed, and write pi dashed is equal to pi by root over m omega. Okay. If I now make this substitution into the expression of total energy, then I get E is equal to omega by 2 summation I equal to 1 to n pi squared pi dash squared plus qi dash squared. So you see, in the new coordinate system, the surface of constant energy is a sphere whose radius is equal to square root of 2e by omega, right? And in this way, now, so since the surface of constant energy is a sphere now, then the number of microstates associated with this particular value of energy will be the surface area of this sphere, which has a radius of 2e by omega, and the possible phase space coordinates. Okay, so I can actually substitute this value of r over here, and then I can calculate the total number of microstates. Okay, so basically I get a hypersphere of radius r equal to 2e by omega, and the volume is basically the solid angle into r to the power d by d. And if I do this, I can calculate omega, and if I take the log of omega, I obtain the entropy in this manner only. Okay, so once this is done, then I can also calculate the energy and the heat capacity as functions of temperature and n. Okay, so I know that del S by del E is equal to 1 by T. So this is del, since S is given by this expression, del S by del E is equal to NkB by E, and we obtain E equal to NkBT. By the way, while deriving the expression of omega, the simplified expression, we had actually taken the thermodynamic limit of n and E going to infinity. Okay, so that's how we had been able to simplify this expression of entropy over here. All right. Okay. And mind you, another important thing is that this transformation is a canonical transformation. So it is something which preserves the volume in phase space. So I mean, one can only go from one coordinate to another coordinate if the transformation is a canonical transformation, because the phase space volume is an important thing, because the phase space volume tells me about the number of accessible microstate my macrostate has. Okay, and if that is changing upon transformation, then those transformations we cannot make while obtaining the total number of microstates. So that is another important constraint which one should keep in mind. Okay, similarly, we can also obtain the joint probability of a single oscillator also. How? By I can sum over the undesired coordinates and momenta of the other n-1 particles. So in the ideal gas, for finding the probability of a particle having a momentum of p1, we had summed over all the other particles while keeping the momentum of that particle fixed. Over here also we do the same thing. We keep the position and momentum coordinate of the particle we are concerned with fixed, and then we sum over all the other coordinates. And in that way we can find the probability. So that's why the probability is equal to omega of n-1 particles and energy of n-1 particles. Energy of n-1 particles being E minus p1 square by 2m minus m omega q1 square by 2, p1 and q1 being the coordinates of the particle I'm concerned with, divided by h into omega n e. This h factor comes in because of normalization and it gets cancelled out. So using the Stirling's approximation, using the thermodynamic limit, that is n going to infinity, and setting this value of energy, we can obtain an expression for the probability of an oscillator having a momentum p1 and q1. Okay, and once I obtain this probability, I can also calculate the mean kinetic energy, which is p square by 2m multiplied by the probability integrated over dq and dp, which turns out to be kBt by 2, and the mean potential energy, which also turns out to be kBt by 2. So this is like the equipartition of energy which we have usually for such systems. Okay. Now moving on to quantum harmonic oscillators. Again, we have a similar concept as the classical one only. So for a quantum harmonic oscillator, the energies have this particular form. The only difference is that the energy levels are discrete, unlike the classical oscillators. Ni is the quantum occupation number for the ith oscillator. Okay, so the ith oscillator can be in any of the energy levels which are defined by Ni. And here also I have to calculate the entropy as a function of total energy. So here is a different approach which we need to apply in case of quantum oscillators, because these are discrete systems. Classical systems are continuous systems. So we had a continuous integral over phase space. Here we don't have a continuous integral over phase space. We have to arrange the discrete oscillators in different ways. So how do we go about that? So the total energy of the set of oscillators is equal to h cross omega summation over I equal to 1 to n ni plus n by 2 factor coming in from this half over here. Okay, This is the total energy of the set of all oscillators. So this is the constraints which my oscillator should satisfy. Okay. Now the summation over the individual quantum numbers, this becomes equal to E by h cross omega minus n by 2. Okay, so n1 plus n2 up to nn, this gives me the sum over all quantum numbers m. So we have to basically, that is the sum over all quantum numbers gives me the total number of energy units which I must have that satisfy these constraints. Okay, so I have capital N number of oscillators and capital M number of energy units which should satisfy the constraint of total energy together. Okay, so the total number of microstates which the system has is the number of possible ways of different m number of energy units into n slots. Or in other words, it is, suppose I function m number of objects using n minus 1 number of balls. So how many ways can I put n minus 1 partitions in a system of m objects placed along a row? So the total number of ways in that can be done is that m plus n minus 1, that is the total number of permutations of the walls and the objects if I consider them as discrete objects, divided by the number of permutations between the objects themselves, which is n factorial, into the number of permutations of the walls, which is n minus 1 factorial. So you can see by this simple expression, I can calculate the total number of microstates that my system should have. Once I know this, I can calculate entropy using this well-known formula. And from entropy, I can get the internal energy using this expression and the heat capacity as well. Okay, using dE by dt equal to C at a constant n. And after I do that, I can also find the probability of finding a particular oscillator at the nth quantum level. And so again, what we again follow the similar steps as earlier. We fix one particular oscillator at the nth quantum level, and we take the permutations of all the other oscillators. So this becomes equal to number of microstates for a system having n minus 1 oscillators with total energy equal to E minus n plus half h plus omega divided by the total number of microstates which you originally had. So if I calculate this quantity, then this is what it turns out to be. And then in the thermodynamic limit of n and m going to infinity, I can simplify this expression further and get this particular value, and from that I can read off my probability Pn. Okay. Now you see that the heat capacities which we get for the classical and the quantum oscillators are different. For the quantum oscillator, the heat capacity is this thing, and for the classical one, the heat capacity was equal to n kVs, right? On the other hand, both are harmonic oscillators. So again, this leads me to the question, how do I go from the classical to the quantum thing? So earlier we had seen that we had taken the limit h cross going to 0 to obtain the classical limit of a quantum system. Here also we do the same thing. We take h cross going to 0. So if I take h cross going to 0 and this exponential, if I Taylor expand it and write it as 1 plus x, then I can substitute the denominator by 1, and this I write as 1 plus h cross omega by kBt minus 1. So this again becomes h cross omega by kBt whole square. So then this quantity and this quantity cancels out, and finally you get C equal to nkb. Okay, which has been what is done over here. So thus you can see that by taking the high temperature limit or the limit h cross going to 0, one can obtain the classical limit of a quantum system, and the classical and quantum heat capacities become the same. All right. So this is some of the problems which I had in store for today. So I think this is not today. So if there are any questions, just let me know, or if not. So are there any questions or doubts, or is there any specific topic which you want me to cover in the next class?
சார் எக்ஸாம்க்கு எப்படி சார் ரிஜிஸ்டர் பண்றது?
Oh, exam register.
Yes sir.
Oh, registration is something which I don't know. Actually, NPTEL team will tell you how to do it. So yeah, so registration, I think your exam is in next month, April. Before that, you have to register for that. So you can contact your instructor or the NPTEL team. They will let you know.
Thank you, sir.
Okay. So is there any specific topic which you want me to cover in the next class, or specific problems which you want to discuss? Or shall I go ahead with the problems which I'm doing? Okay, so if not, then in the next class I can move on to canonical ensembles, and I can also discuss a few problems on Bose-Einstein statistics. The derivation I have done today only, so I won't be doing that in the next class. I can discuss a few problems on that as well. So with that, I can end the class today. So thank you all for coming in, and I will see you next week.
Thank you, sir.
Okay, bye then.